All right, so last time we left off with just a few examples left in this section, and this was one of them. We had skipped it, and we had skipped it because the others were a little bit more straightforward, and this one involved a little bit more work. Now, on all the other ones that we had looked at in this section, if they weren't directly integrable, we did what process? U substitution. And generally speaking, the U substitution, if you've got a denominator, is the denominator, right? But you very quickly see that if you let the denominator be u in this one, you've still got a whole bunch of stuff on the numerator side of this that's not helpful when you do your derivative. Agreed? Any other ideas that you remember from integrating in Calc 1? Did you have ideas, Jordan?
Can you split it up into 3 different pieces?
That's called partial fractions, and we're going to do that later in Calc 2, but depending on, did you take Calc 1 in high school?
I just took calculus.
You took calculus at a different university?
Well,
or here?
no, AB.
Okay, that's why. So in our textbook, we haven't learned partial fractions yet. And we actually don't end up needing them on this one. Yeah. Do you guys remember any other methods?
You can separate it out.
I have an idea.
Okay, hang on, Aaron, what did you want to suggest?
You can separate it out like numerator times 1 over x.
That won't work because they can't do that. You can't separate the denominator apart. X minus 2 is a whole expression. Yeah.
Could you bring the...
Jordan, did you have a suggestion?
There's some, like, make it 2 equations that are being multiplied together. Like,
I'm not sure we can do that. That would work for us. You mean like factoring the numerator?
yeah.
Is that what you had in mind? Factoring the numerator is a legitimate possibility. It works really well when you're doing some of the other methods, but it still won't work for this one. Did you have a suggestion, Janet?
Could you bring the denominator up?
Again, bring the denominator up is going to do kind of what Aaron's problem is that I have to bring all of it up with a -1 exponent. And so I still can't simplify anything with it. Okay. There's one other method you learned in Calc 1, and usually people are not super fond of it, but it's not difficult. It's an algebra concept. We're going to actually divide. We're going to use long division, and we're going to divide the numerator by the denominator. Okay? So you may not have seen it. That's fine. It's not used all that frequently, but it is a handy tool. The reason that this one sort of lends itself to that idea is because the numerator's degree is what? Somebody said it. Parker? No, the numerator. What's the degree in the numerator? It's a 2. Remember, numerator is the highest exponent. The degree of the numerator is 2, and the degree in the denominator is actually only 1. So the degree on top's larger, or even if it were equal to, we could do this. But the issue being that the degree on the denominator is not larger. So using long division is a good option. So let's remind ourselves how to do long division with this. So we take a look at the division, a lot like you did division back in, 3rd or 4th grade. And you say, how many times does x go into 2x squared? 2x. And another way to ask yourself that question is, what do I need to multiply x by to get 2x squared? So that answer is 2x. Use a different color. And then you multiply the 2x by the x minus 2. So 2x times x is 2x squared. That's why we chose it. What is 2x times -2? -4x. And then what did you do in long division way back in 3rd and 4th grade? Next, you subtract, right? So subtraction for us actually means changing both signs. I mean, that is subtraction. So that's why the 2x squareds, we wanted them to line up exactly, is because when we subtract, these actually are eliminated. They add to 0. What about the next piece? What's 7x, and then now it's plus 4x? 11x, and then I'm going to pull my -3 down. And we're not done because I still have a degree that's the same, right? I have 11x minus 3, which is a degree 1 polynomial, and I've still got x minus 2 on the outside, which is a degree 1 polynomial, so I can do one more step. How many do I need to multiply x by to get 11x? 11. Okay, so we go through, we do the multiplication, I get 11x down here, and then I have 11 times -2. -22. And then what do I do? Subtract by changing my signs, exactly. Perfect. All right then, so what happens next? Let me see that way. Those 11x's cancel, yeah, and I get 19. Now here's the cool thing about this. Notice then that what that means I can do is I can rewrite this fraction 2x squared plus 7x minus 3 over x minus 2 as 2x plus 11 plus 19 over x minus 2. Do you guys remember that? It's an algebra idea. And then all those pieces we can integrate. Some of them using rules that you've used before, and then the last piece, the 19 over x minus 2, using our new rule with logs. So what is the antiderivative of 2x? Yeah, 2x squared over 2, or x squared. What's the antiderivative of 11? 11x, right? And then what do I do with that 19 over x minus 2? The antiderivative. Okay, but what is the antiderivative there? I'll start for you. 19 doesn't change. There you go. Natural log, because I've got a value of the x in the denominator, and that's natural log, and it's absolute value, right, Taylor? Yeah. I have x minus 2. I'm running out of space. Let me move this over. Okay. So I have the natural log of the absolute value of x minus 2 plus c. Thank you. So if I wait long enough, you're going to be like, she's waiting for something. What is it? Plus c. So there's really not a lot of calculus different here. The difference is the algebra at the beginning. You've got long division. Any questions on that one? Okay. Now, I had mentioned before when we were doing your antiderivative sheet, grab it out if you don't have it out right now, this antiderivative sheet that I gave you last time. You had filled in the front half, which was 1 through 11, even though 8 was duplicated, so there's 12 of them, and I get that, yeah. But we filled in the front half of the sheet. So we hadn't done anything on the back yet. You can fill in the first one on the back, number 12, very quickly. What is the antiderivative of 1 over x? Yeah, natural log absolute value x. And then the next 4 on this sheet are going to actually be coming from this particular slide that we're on right now. Now the first 2 we already have done before, so let's fill those in quickly. What's the antiderivative of sine of x? Negative cosine of x plus c. And the antiderivative of cosine x? Sine x plus c. And on this antiderivative sheet, those were 7 and 8. Okay? But now we're going to be looking at 13 through 16. And we're going to fill in the rest of those. So I'm going to give you what those look like, and they involve logs. All right? So the tangent is the negative natural log of the absolute value of cosine of x plus c. As in most cases, if tangent looks like that, cotangent is going to look quite similar. It's going to be the opposite sign, so it's positive. Instead of cosine, what do you think it might be? It's sine. And then plus c. Secant of x is the natural log, the absolute value, of secant x plus tangent x plus c. And the cosecant is the negative natural log of the absolute value of cosecant x plus cotangent x plus c. So I'm about to make your day. Are you ready? Are you ready for your day to be made? Yeah? Okay. When you do that antiderivative gateway exam, or I'm sorry, we call it a basic skills exam in like 2 months or whatever, it's not quite that far away, but the antiderivative one, the second one, you don't have to have through 16 memorized. Okay? So you only have to go through 12. All right? So when you do your tests on these, you can take this sheet and you can use it. So I don't need you to memorize these last 4. You got to know the first 2, but you guys already know the first 2. These last 4, you can just hold tight to, okay? And use your sheet to remember them. Sound good? All right. All right, let's do a couple of examples with this information and try this one out. All Okay, so we're going to find the indefinite integral of the secant of x over 2. So this almost looks like just secant of x, right? And you've got an antiderivative rule for it. I just had you write it down, and it looked something like natural log of the absolute value and some stuff, right? Okay. So we're going to use that, obviously. What else do we have to use here, though? Yeah, the u substitution. So what would you like for u to be, Caesar?
2.
Close. It'll be part of that. I mean, 2 is part of it. X over 2. Because what I really want is I really want to replace the x over 2 part with one single variable, because then it looks just like the rule I have. Okay? So then what's my derivative? I think it's 1/2, isn't it? Right? Yeah. I mean, this is just, x over 2 is just a 1/2 of x. So the derivative is 1/2 dx. Now, there's not actually a 1/2 dx in my problem. So we did this last time where I multiplied that 1/2 to become 2 du on the other side. So up here in the problem, I've got 2 at the beginning, and I've got my du at the end, and that replaced the dx. Right? Dx gets replaced by 2 du. And in the middle, I've got the secant still, because that did not change, but now I've got the secant of u instead of x over 2. Okay, so flip back real quick. What is the antiderivative of secant of u? Natural log of the absolute value of secant, in this case it'll be u, plus the tangent of u plus c. Am I done? No. What's missing? Or what do I need to do? Yeah, I need to replace the u's with x over 2.
So can you not move the 2 back up there, like on the outside of the bracket, since it's a natural log?
Oh, you mean, could you move the 2 that's the coefficient to make it an exponent? You could. It wouldn't hurt anything. If you did express it that way, you could ignore the absolute values then, because when you square things, they become positive. Yes,
So
Parker?
the derivative of x over 2, is that like just like saying 1/2 x?
Exactly. Because x divided by 2 is the same as half of x. Yep. Any other questions on this one? Not too bad, right? Okay, we got 2 more. This one doesn't quite look like any of them directly. You might be tempted to do something like actually divide the cosine and the sine, but you can't, because the denominator has addition in that, so there's no way to separate the sine and the 1 in the denominator and simplify the numerator any. That's not possible. So I'm certainly thinking long division, like we did in the problem, the first one today, doesn't seem like it makes any sense. So what? What do we do now?
We can use u substitution.
It's our best friend, isn't it? We've used it a lot. Do you know what you would like to let the u value be, Jordan? The bottom, yeah. We do that a lot too, right? That's the common feature. So if I let the denominator, that is 1 plus sine of t, be equal to u, what would du be?
Cosine.
And how nice is that? Because that's part of your problem, isn't it? Cosine of t, dt. Let's write that better. Which is exactly what you have on top and to the side. The cosine t dt is right here. So that piece now is du. So I can rewrite this then as the integral of 1 over u du. And what's the antiderivative of 1 over u? Natural log of the absolute value of u plus c. And then I need to do my replacement back, right? Natural log. Now, you actually have an option here. You don't really have to do absolute values. If you do, it doesn't hurt anything. But if you're looking in the back of the book, you're for sure going to see them take out those absolute values. Any idea of why you don't need them? Or 0, right? Yeah, sign values, remember we talked about this, I think the first day of class, they go between -1 and 1. Right? They go back and forth between -1 and 1. Well, that means that the smallest sign value is -1, and you've got +1 already inside that parentheses with it. So I can't get this 1 plus sine t to be negative. So the absolute values are sort of overkill. Again, you can leave them, it doesn't hurt anything. But if you see them removed, that's actually why they would have been removed here. Make sense? All right. All right, one more in this section. We've got, or we're going to evaluate the definite integral. So we haven't done a definite integral yet, but we're going to do it now. And we've got 1 plus the natural log of x quantity squared over x and then dx. So what would you like to try? U substitution sounds like a good idea. What do you think you might want to let u be?
1 plus natural log.
That sounds like a good plan. And why in the world do we want to do that? The derivative is 1 over x. Also, we talked about last time, you don't have a way of taking an antiderivative of natural log of x yet. So you've got to get that natural log of x to not appear in whatever it is you're finally trying to take the antiderivative of. The only way you have right now to do that is u substitution. All right, so you already told me that du is 1 over x dx, right? Okay, so what I'm going to do, there's a couple of ways to do this, but I will tell you my default is I'm leaving the 1 and the e off of the problem for now. I'm just going to leave them off completely. So every time I write my integral now, it's going to look like there are not limits to evaluate them at, okay? No endpoints. All right, so what will this be rewritten as? Well, u squared is correct, but the x isn't there anymore, right? The over x part and the dx actually, from here, get replaced by du. So I really only have the integral of u squared, which I like because it's one of the rules that I know, and you guys know that very well. What is the antiderivative then of u squared? U cubed over 3, or 1/3 u cubed, either way. We do have a plus c. You can put it here or you can put it at the end. As long as it's at the end, I'm okay with that. But you're not done, right? If the 1 and the e had not been a part of this, if this were not a definite integral, then you would be finished after you put the u's, replace the u's with the x's back in the problem. But I need to evaluate it at 1 and e. But 1 and e were actually limits of integration on the variable x. And I've got a variable u in my problem right now. Everybody tracking with me on that? So in order to use 1 and e, one way to do that is to change everything back into x's and then use 1 and e. And that's how I deal with it, okay? So I'm going to change the u back into, and I'm going to write this as 1/3 in the front just to have it sort of pulled out. I've got then the 1 plus the natural log of x quantity cubed. Again, you can put the plus c, but we're actually not going to need it on this one. Why? Do you know why? Because it's a definite integral that we're evaluating. We only need it when we've got an indefinite integral. So on this particular one, if you leave the plus c off even at this step, you're okay, because in the end, you're not going to have a c involved. Okay, so this looks good. Now what? Oh, sorry. Yes, from the original 1 and e in the problem back up here. Right up there. That's where those came from. All right then, so we're going to evaluate this thing. I'm going to move over here so I have more space. I have 1/3. And I'm going to put in, let's see, 1 plus natural log of e, quantity cubed. So that's evaluating at the point e, minus the 1/3 of 1 plus the natural log of 1, quantity cubed. All right, so I gave you back in section 1 some properties of logs. You may or may not have remembered them at that point, but you have them now. Do you remember what the natural log of e is? Natural log of e is 1. What's the natural log of 1? 0. That one's 0. So this value is actually the number 1, and this value is actually the number 0. So what I actually have here is I have 1/3 of 2 cubed minus 1/3, in essence, of 1 cubed. Because I have 1 plus 1 on the first parenthesis, and I have 1 plus 0 on the second. What's 2 cubed? 8. So the first piece is 8/3. Obviously, 1 cubed is 1, so this is minus 1/3. So what's my grand total at the end? 7/3. Any questions on that one? All right.